Cosmology has changed forever with the launch of James Webb on Christmas Day 2021. Ever since it opened its impressively sharp, high-resolution infrared eyes, James Webb looked back at some of the earliest stages of the universe, gathering sharp, pristine, and beautiful insights into early star and galaxy formation. It provided insights into the formation of planetary systems, including our own solar system. But, in some sense, James Webb was almost too good, far exceeding all hopes and expectations. Astronomers expected to find some infant galaxies with Webb, but they didn't expect to find so many. Webb's unprecedentedly deep views revealed a colossal surprise, a bunch of seemingly impossible early galaxies. Even at these earliest times, these galaxies were too big, bright, and numerous to explain, some of which are even older than the universe itself. Our best cosmic predictions, based on Lambda Cold Dark Matter, the standard model of cosmology, didn't anticipate what James Webb saw. In other words, discoveries made by James Webb could shake our understanding of galactic history, challenging the foundations of the Big Bang and all of modern cosmology. Join us as we delve deep into how James Webb just found massive structures that could defy our current theories of the universe. The farther and farther back into the distant universe we look, we have a picture of what we expect to see. At some point, we should find the first and earliest bright, large, luminous galaxy. We should see their number density rapidly decrease as we approach that limit. Before that, we should find only smaller and less evolved galaxies, decreasing in number and number density until we find the very first among those. Before that, we should only see individual star clusters and protogalaxies, and these should be extremely blue and primitive, existing in low number densities. The farther back we go, there should truly be a time where the very first stars and star clusters of all appear. Beyond that, there should be no luminous sources at all to observe, excepting the Big Bang's leftover glow itself. When we look into these deep depths of the universe and examine these galaxies, we're basically asking the universe, how did you grow up and come to be the way you are today? Given that we have a model of the universe, a mix of dark matter, normal matter, dark energy, and a little bit of radiation, we can arrive at predictions for what we expect to see in the universe at any given time. Looking at these distant objects with the James Webb Space Telescope and its spectroscopic capabilities, in particular, allows us to test that model and to see if we truly understand the universe we inhabit, or if and how we have to revise our picture of the cosmos. The James Webb Space Telescope is changing astronomy in many ways, from peering into the atmosphere of exoplanets to capturing stunning images of distant cosmic phenomena. Perhaps its greatest scientific contribution is its ability to observe galaxies that are so distant that looking at them is like looking back in time. Projects like Webb's CR, or Cosmic Evolution Early Release Science Survey, are scanning the sky to pick out some of the oldest galaxies we've ever seen. When scientists first turned Webb toward apparently empty patches of sky to look for these distant galaxies, they found something very strange. They didn't just find a few very old galaxies dating back just a few 100 million years after the Big Bang. They found far more of these galaxies than anyone had predicted. According to Mel Bagley of the University of Texas, one of the leading SEER researchers, the theoretical models didn't predict that these should be there. "We still don't yet know how you can see a galaxy that bright that early," said Bagley. One particular galaxy jumped out of the CIR data straight away, Maisy's galaxy, named after the daughter of Stephen Felstein, one of the researchers. It is 13 billion years old, making it one of the oldest galaxies ever observed. It is much brighter and much bluer than anyone predicted. As Bagley said, when we found Maisy's galaxy, the surprising part was, how is it in the universe? It's exciting that this is the universe we live in, a universe with a ton more galaxies than we thought. Webb is able to detect extremely distant galaxies because its instruments operate in the infrared wavelength. A small handful of extremely distant galaxies had been detected previously by the Hubble Space Telescope, which operates primarily in the optical light wavelength, equivalent to what human eyes can see. But as galaxies move further away from us due to the expansion of the universe, their light is shifted toward the red end of the spectrum in a process called redshift. The extremely distant galaxies that early universe researchers are interested in have light that is redshifted so far that it is no longer visible in the optical and can only be seen in the infrared. Hubble's instruments were pushed to the limits to detect even a few of these galaxies, while Webb was able to detect many of them incredibly quickly, within a few days of the telescope beginning its science operations. When discussing these galaxies, scientists typically talk about them in terms of their age, rather than their distance. Researchers describe a galaxy as being from the first few 100 million years after the Big Bang, rather than being located billions of miles from Earth. That's also because of the expansion of the universe, creating a moving frame of reference that makes it hard to describe distance meaningfully. Examples include galaxies like Maisy's galaxy, described as being 13 billion years old. The light has traveled 13 billion years to get to us, but if we could see Maisy's galaxy today, it is much, much further away, because in that time, the universe has kept expanding and accelerated its expansion. The time the light has spent traveling to us gives us more concrete information about when in the universe we're observing these galaxies. Initial estimations of the redshift and thus age of Maisy's galaxy were based on photometry, analyzing brightness in images while using a small number of wide-frequency filters. These calculations suggested the galaxy had a redshift of 11.8, but Finkelstein and the Seer team wanted a more accurate age estimation. To do this, they made follow-up observations with James Webb's near-infrared spectrograph, or NIRSPEC for short. NIRSPEC allowed Finkelstein and colleagues to look at spectral lines created in light data dictated by the absorptions and emissions of chemical elements at specific wavelengths. From there, they could pinpoint the actual redshift of Maisy's galaxy type. It appeared to be 11.4. This means Maisy's galaxy is technically seen more recently in the universe than initially estimated, by a factor of tens of millions of years. Nonetheless, it is still considered immensely old. James Webb captured the galaxy as it was just 390 million years after the Big Bang. This impressive age places Maisy's galaxy among the 4 oldest galaxies in the universe that have had their ages confirmed by spectroscopy. Spectroscopy is a technique that splits light into its component frequencies to better reveal its brightness, heat, and chemical composition. While such galaxies don't yet pose problems for leading models of cosmology, they suggest that galactic formation began earlier and proceeded faster than expected in the universe. Theorists had previously predicted that the universe began churning out galaxies at the ripe age of 1 billion years after the Big Bang. As Fabio Picucci of the Harvard-Smithsonian Center for Astrophysics said, "We're seeing a rise of massive galaxies faster than we thought." The ages of some of these early galaxies are estimated at just tens of millions of years. This could have implications for large structures of dark matter known as halos that sculpted early galaxies, and for the nature of dark matter particles themselves. One of the big open questions is, what is dark matter? Says Sandro Ticella of the University of Cambridge. The first generation of galaxies is a sensitive probe for different dark matter models. On the other hand, we should be cautioned that some problematic and potentially model-busting early universe candidate galaxies still remain. Scientists had already produced models of what early galaxies would be like, and Webb contradicted them almost immediately. As soon as James Webb began looking for early galaxies, it found far more of them than anyone had predicted, and found that they were much brighter too. Light is a double-edged sword in the context of these galaxies. It's what lets us study them, but there's so much more of it than astronomers would have expected. The brightness of a galaxy can be related to its mass because a galaxy's light comes from stars. Assuming a certain average brightness and mass of a star, you can roughly estimate the mass of a galaxy. But much of the modeling astronomers have done up to this point has led them to believe that there wasn't enough time for galaxies to get this massive in so little time. According to Jorge Moreno, an associate professor of astronomy at Pomona College, it's like if you went to a kindergarten and you saw a teenager. What's more, today, most galaxies are separated into 2 types: spirals, which are disk-like with arms of dust and gas, and ellipticals, which are more like spheres of smooth light. Until now, scientists thought that any galaxies from this relatively early period in the history of the universe would have been too young to have been forced into that binary yet. Instead, astronomers thought the galaxies would be blobs. But under James Webb's views, some of the early galaxies look a lot like galaxies in the local universe. They seem to have added structure, and maybe even spiral arms. That wasn't something we really expected, Marino notes. The high level of structure and brightness in these galaxies is leading some astrophysicists to question the age of the universe in an attempt to explain the impossible. Massive galaxies existing so early in the timeline of the universe. A researcher has posited that the universe is roughly twice as old as previously believed, pushing the age of the universe from a spry 13.8 billion years old to roughly 26.7 billion years old. That's an interesting scenario, but it doesn't correspond to the evidence at hand, says Marino. Up to now, there's currently no consensus on what is the root of the discrepancy between the models we have and the data we observe with Webb. The answer could be related to dark matter and its role in the early universe. Or it could be that the way early galaxies were formed was spurred on by forces that haven't been considered yet. However, it's worth noting that even before the James Webb Space Telescope, scientists knew that the early universe was a very different place from the universe today. Its galaxies were made almost entirely of hydrogen and helium, shaped by tendrils of dark matter, and hosted enormous bright stars that lived fast and died young. While the laws of physics haven't changed over the past billions of years, the scale of the universe has, and that affects how those physical laws apply to galaxies. When the universe was smaller and denser, that affected the ways in which stars form in complex ways. As Bagley explained, if the universe is smaller, the density inside galaxies and outside galaxies is probably higher. If it's dense and hot, the gas won't collapse to form stars. If it's dense and cold, then you could get a ton more stars. Another way in which the early universe was fundamentally different is in its overall chemical composition. Heavy elements like metals were almost entirely absent in the early universe because these elements were primarily formed within stars and spread by their explosive deaths, called supernova. It took several generations of stars to spread these heavier elements through the universe and to be absorbed into stars similar to those we see today. The hypothetical earliest stars in existence are referred to as population 3 stars. Today's young stars are population 1 stars, and the numbering counts backward in age. The hypothetical earliest stars were much bigger, heavier, and bluer than stars today, giving off more ionizing radiation. These differences are because of the way stars generate heat and light in a process called fusion. If a star is made only of hydrogen and helium, to do fusion, the star has to be hotter and denser than a star that has carbon, nitrogen, oxygen. As Bagley explained, there's a different chemical pathway to create fusion, and that requires a larger size and more mass to support it. No one has ever observed a population 3 star before, and finding one is one of the holy grails of modern astronomy. But scientists believe it could be possible to find one using Webb. Anyway, James Webb was built primarily to transform our understanding of the early universe. Telltale evidence gathered by the James Webb Space Telescope suggests we're closer than ever before to finding elusive first stars of the universe. All of this discussion of billion-year-old history might seem rather abstract, but in fact, it's directly relevant to understanding the universe as we see it today. The James Webb Space Telescope is revealing in greater detail than ever before. That's because astronomy operates on such long time scales that we can't watch objects like galaxies across their lifespans. Most galaxies we see around us today look like the Milky Way, but we can't see them develop over time. To study that development, we need to look for distant and ancient galaxies, which Bagley refers to as baby pictures of the Milky Way. This is all about understanding how our Milky Way formed. It sounds cliché, but before we can understand where we are and where we're going, we need to understand where we came from. In addition, on the hunt for alien civilization, NASA has just revealed that 17 discovered exoplanets could house subsurface oceans buried below thick sheets of ice. These worlds, much like the icy moons of Jupiter, could be promising places to search for biosignatures, chemical signs of life. While the exact composition of these worlds remains unclear, estimates of their surface temperatures from previous studies point them being significantly colder than Earth. They're also each less dense than Earth, despite being roughly the same size as our planet. As Lynn Quick of NASA's GED Space Flight Center said in a statement, "Our analyses predict that these 17 worlds may have ice-covered surfaces, but receive enough internal heating from the decay of radioactive elements and tidal forces from their host stars to maintain internal oceans." In other words, while their host stars may not provide conditions warm enough to keep water in liquid form on their surfaces, these planets may exhibit processes that can generate heat below their surface. The stretching and compression of rock inside a planet, as it gravitationally interacts with its sun, for instance, could provide significant amounts of internal heat enough to sustain a subsurface ocean. The radioactive decay of heavy elements inside the core of a planet can provide intrinsic heat as well. Thanks to the amount of internal heating they experience, all planets in our study could also exhibit cryovolcanic eruptions in the form of geyser-like plumes. Quick said, "Cryovolcanism, meaning in short ice volcanoes." The study drew on what we know from the geyser activity of two of Jupiter's moons, Europa and Enceladus. Two of the exoplanets named in the research, Proxima Centauri b and LHS 1140b, were particularly promising candidates for having oceans relatively near the surface. Since our models predict that oceans could be found relatively close to the surfaces of Proxima Centauri b and LHS 1140b, and their rate of geyser activity could exceed Europa's by hundreds to thousands of times, telescopes are most likely to detect geological activity on these planets, said Quick. Follow-up observations of these worlds will likely include astronomers capturing the emission spectra of light traveling through these planets' atmospheres. Chemicals and molecules erupted into the atmosphere from cryovolcanic activity may hold clues as to whether life might exist in the cold, dark depths of these worlds. In a one-of-a-kind event, scientists just announced that Mars's atmosphere, once as thick as, if not thicker than Earth's today, is leaking into space. About 11 kilograms of our Mars atmosphere is pushed away every second by the incessant solar wind, the speedy stream of charged particles routinely blasted from the sun, which pervade the solar system and even reach beyond Pluto. But for a rare 2 days last December, some of that wind went away. Its sudden and dramatic disappearance caused the atmosphere on Mars's sun-facing side to swell by nearly 4 times its usual size, from its usual 800 kilometers to over 3,000 kilometers. The peculiar event was recorded by a NASA orbiter named MAVEN, short for Mars Atmosphere and Volatile Evolution, which has been observing both Mars's atmosphere and its response to the sun's behavior since 2014. MAVEN's data showed other aspects of the Martian system, including the teardrop-shaped magnetosphere, the bow shock, and the ionosphere, expanded similarly. As Jasper Holokas, a professor of physics and astronomy at the University of Iowa and a member of the MAVEN team, said, "We're really off the charts here. This is something that we haven't seen at Mars before." With MAVEN, the atypical episode, the first in nearly a decade of MAVEN's career, occurred after a fast-moving region of a solar wind overtook its slower counterpart and swept up the lad's material, leaving behind a sparse region. The emptied storm reached Mars on December 25, 2022, giving scientists a thrilling front-row seat to watch the planet's atmosphere balloon out the way it might have been if it were circling a less windy star. According to Halikas, who is leading a new study, this was a Christmas present for us. Nature set up this perfect science experiment with MAVEN's data of the unexpected dynamics on Mars. Halikas and his colleagues studied how extreme solar events and their absence influence the planet's atmosphere, an insight valuable to understanding its evolution. The findings also have implications for our understanding of Earth-like planets outside our solar system and how they interact with their host stars. The team shared on Monday, "We could look under the hood at what physics is going on, how the dynamics are working, and really get a sense of those details," said MAVEN team member Skylar Shaver of the Laboratory for Atmospheric and Space Physics in Boulder. 2 days after the almost vacant storm passed Mars, the atmosphere around the red planet settled down to its original state once again, but not before bouncing a little like a jiggling plate of jello. A similar storm struck Earth in 1999, when our planet's atmosphere grew to 5 times its normal size. But there is an often orbiting spacecraft positioned as well as MAVEN is now to study such events, the new atlas reported. That most recent safe mode entrance was slightly worrying, as it persisted for longer than the previous 2 dips. It wasn't too worrying, though, because first of all, this isn't the first time Hubble's gyros have raised issues leading to a shutdown. And secondly, maybe most importantly, the observatory can actually function with only 1 gyroscope. The team just uses 3 because it maximizes efficiency, though it's been over 3 decades since Hubble began exploring the vibrant reaches of our universe, and though a new observatory in town has been catching most of the spotlight recently, this Reynolds Wrap-looking telescope is surely not finished yet. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.